Hello everyone, I'm Jiafan Wang from Department of Information Engineering, the Chinese University of Hong Kong. I'm going to present the paper Forward and Backward Secure Range Searchable Symmetric Encryption. This is a joint work with my supervisor, Professor Sherman Chang. The ever-growing data cause great pressure on local storage. An attractive solution is to outsource them to the cloud server. How to secure outsourced data while enabling efficient search on them becomes an interesting problem. For efficiency and security, it is natural to index and encrypt the data respectively before outsourcing them. Searchable Symmetric Encryption, or SSE, is a useful cryptographic primitive here. An SSE client could search for files matching a specific keyword from his encrypted data by creating the corresponding search token. The token enables the server to do the search. The dynamic version of SSE, or DSSE, further enables the client to update his outsourced data. A new keyword file pair could be inserted with an update token. To mitigate file injection attack, DSSE requires forward security. Forward security ensures that the keyword in any update will not be revealed until the next search on it. Searching for a range of values is a common query type, serving as a basic function of SQL queries over encrypted databases. For this case, the keyword space becomes a domain of numeric values. Range queries over encrypted data should be supported in a way that is more efficient than naively searching each value in the range one by one. An approach is to build a tree-like index on top of searchable encryption and reduce a range query to multiple single keyword searches. Weber et al. And Demetrius et al. Initiated this study. They presented diverse indices, yet their schemes are not dynamic. That is, not supporting the insertion of keyword file pairs. Zhuo et al. Aimed at range DSSE, yet their construction requiring efficient public key operations due to their building blocks. Worse still, the claim of forward security in one of their schemes is problematic. We demonstrate an adaptive file injection attack against it in our paper. Their subsequent work, which is also subsequent to ours, fixes the problem with a scheme using homomorphically encrypted file index. The file index is actually a bit vector with each slot denoting the existence of a file. It limits the maximum number of files and makes the updates restrictive. We summarize a framework of range DSSE with a running example using a binary tree index and vector range covering technicals by Kiayas et al. To set up, the keyword space is broken into subranges. We associate a unique keyword to each of them. We run DSSE setup on the actual keyword and the keywords of subranges, as shown in the example. To search, the target range is broken into subranges or keywords. For example, we break the range 1-3 into keyword 1 and subrange 2-3. We run DSSE search on them for the range query. For update, we find out any subranges covering the keyword to be updated. For updating keyword 2 in the example, subranges 2-3 and 1-2-3-4 are figured out. And we run DSSE update on the actual keywords and those associated to the covering subranges. We obtain our modular construction, MoRSE, by instantiating the framework with any typical DSSE. The modular design avoids design-specific problems of prior works, for example, the inefficiency due to specific building blocks. For update, MoRSE runs DSSE's update for times logarithmic in the keyword space size, which is essentially the height of the tree index. For search, the client needs to figure out the covering subranges, which can be done in time logarithmic in the range size, though the server needs to run multiple times of DSSE search. The sum of them is typically the number of matches, as these subranges have low overlaps. Notably, more RSE inherits forward privacy from its underlying DSSE, because the updates for each keyword or subrange is carried out independently. Before presenting our second construction, we recall the storage overhead of single keyword forward secure DSSE. For optimal round trip, it doesn't outsource the state, but keeps a state per keyword, which usually consists of a key and an update counter. For an update of a keyword, the client will use the PRF value evaluating its key and counter to determine the address to store it. Then, the update counter is increased by 1 to ensure the next address is still pseudo-random. When searching for a keyword, its key will be revealed to the server. Meanwhile, a new key will be picked and stored locally to ensure the subsequent update will not be exposed due to any previous search. Thus, the client of forward secure DSSE needs to store states as many as the number of keywords. Consequently, for range DSSE with tree index, the client storage will become around twice of the keywords as it treats its subrange as a keyword. Our second range DSSE construction, R², reduces the client storage due to state maintenance by not storing state for any subrange until it has been searched for. We explain how to ensure forward security when updating a subrange with no state. For an unsearched subrange, its key would be the PRF value inputting itself, which can be derived on the fly. R² computes its update counter as the sum of counters of its descendant nodes, which are stored as per single keyword DSSE. The address to store the update of the subrange is still based on its key and counters. Only after its first search will a new key be selected and stored. For example, if 01 has not been searched for, its key is PRF01 and its counter is the sum of zeros and ones. As no state will be stored for any unsearched subrange, R² has the same client storage as the forward secure DSSE when no range query has been issued. The client storage increases with the number of searched range, indicating that R² is suitable when range queries are required yet not frequent. In general, the number of states stored by the client is the number of keywords plus the number of searched subranges. In addition, it takes time linear in the keywords for the client to calculate the counters for the first search of any subranges. Backward security is another security notion requiring searches concerning any deleted keyword file pair not to reveal the deleted file. Bolster et al. Defined 3 levels of backward security, differently confining the information leaked during updates and searches of a single keyword DSSE. We observe that the definition of Bolster et al. Cannot be applied to range DSSE directly, as searches on subranges may have overlapped results of keywords. Considering this subtlety, we extend the definition of 3 levels to range DSSE. Meanwhile, we show that the 2 round-trip transformation for backward privacy by Bolster et al. Can be applied to our more RSE and R². Please check our paper for details. We implement our more RSE and R² with a keyword space of over 1 million keywords. We also compare the performance to the recent construction FBDSSE-RQ. The time for updates and search demonstrates the efficiency of our constructions. In addition, we evaluate the client-side storage to show the advantage of R-square. We randomly make range queries before measuring the number of states stored in the client side. The result shows that R-square indeed saves the client storage. To sum up, following our framework of range DSSE, we propose a modular construction that avoids design-specific problems of prior works, and a specific construction with reduced client-side storage. Both of them realize forward and backward security and practical efficiency. In addition, centering around range DSSE, this work provides a mini SOK of existing work, a new file injection attack that refutes a previous scheme, and a refined definition of backward security. There are many future works. The first is how to support multiple clients. Our work in Usenix Security this year provides a generic construction that upgrades DSSE with multi-writer support. It is expected to see whether we can upgrade range DSSE. The second direction is the attack mitigation. We are aware of attacks against a range search over encrypted data, which often exploits the volume pattern. We may make range DSSE volume hiding as a mitigation. The next talk by Endo and George will discuss the cost of volume hiding. Finally, we expect to see more expressive query types over encrypted data based on range. For example, the last talk by Espirito et al. Will study aggregate range queries. Thank you for listening and feel free to contact us.